partial x2 and partial phi y, partial x second. So it's the total derivative of this scalar field. Okay. And I know that I can treat this scalar field as the total derivative of the phi as well actually. Okay. So in other words, if I have been given phi, okay, and I compute the fresh derivative of this, for example, phi, and evaluate it at A, and what? And compute it on H. So it's going to be what? The gradient of the phi evaluated at A dotted with H. Okay. Which you can also see, so think about it. You can also interpret this expression. So gradient of phi is telling you what, so it's giving you the total. So if you take a point A, okay, and you take a point phi of A, for example, onto the surface, I mean if you interpret that as a surface, then you can change, you can compute the change in all directions. That's what this gradient is going to tell you, because it's the fresh derivative, right? But now I'm taking the dot product of this with a particular vector h actually. So in other words, I'm saying that how much of the change in the phi is happening in the direction of the h actually. So that's like a directional derivative actually. You can also interpret it as you're computing the directional derivative in the direction of the h actually. Okay? Why this is important? Because let me tell you something. Imagine you have, so in one dimension you have this substitution rule. So whenever you have this x and the square root of say 1 plus x square and dx, I'll be very happy. Okay? Because I'm going to say derivative bar pada. You know, derivative bar pada. What do you mean by bar pada? Okay? Derivative bar pada. Basically, what does this mean? I mean, the general form of this is going to be that, you know, you have a function, composition of a function f of g of x, and you have a g prime of x dx here. And I mean, if you see, like, I can also treat this as informally that it's a derivative of g of x. So I'm integrating f of g of x with respect to derivative of g of x, and I know integrating such functions is very easy. It's very easy. Okay. So in other words, I'm saying, you know, if this function can be written as the differential of some function, because if this is the case, then integrating such function or with respect to such functions is very easy. So we want to do something similar in this domain, you know, higher dimension, something really similar. Higher dimension actually. Okay? मैं get rid of फर्क क्या नहीं होता ही सिर्फ g. So what would be the output? So you're gonna be g of b minus g of a. So let me write it explicitly. So imagine I have a function f that I want to integrate, you know, f of x that I want to integrate with respect to dx. So this is in one dimension. And I can write this entire function as differential of some g of x actually. So it would be very easy to compute the derivative. So g of b minus g of a. So it's like, you know, fundamental theorem of calculus, application of the fundamental theorem of calculus actually. Take it? So you want to do the precisely same. Now imagine I have a gradient field, which is a gradient of a scalar field, and I would like to integrate such a scalar field actually. Okay. So I would like to write this result in the form of a theorem, and this theorem is, you know, we call it as he is calling it the second fundamental theorem of line integrals. We are heading towards the fundamental theorem of line integrals. So So obviously we're going to assume the fundamental theorem of calculus in one dimension. Okay. We'll probably use it and we'll try to prove the second fundamental theorem of line integrals. Right? So what does this say? So imagine you have f that is a gradient field. So it's a gradient of a scalar field. Okay? Okay. Defined on an open U, that is obviously a subset of Rn. Okay? And let's take 2 points A and B from this domain U. Okay? And imagine you have a curve C. Okay? That also falls in the domain of the U. Why we want this curve to stay in the domain of the U? Because I want to operate f on theta. Imagine, the integration, the definition of integrating the scalar field involves that f should be operated onto the P of t. Now f can operate onto the P of t, in other words the path, if the path is sitting inside the domain of the definition of the scalar field. The first picture that I made actually, that you have a scalar field defined on a domain and you have a curve inside it actually. Okay, let C be a rectifiable, okay, curve segment. Okay, from A to B. Which A to B? These two A to B. So I have this domain U, and I'm saying that these are the 2 points A to B, and I have a curve that joins them. That's what I'm saying. And this entire U is the domain of the scalar field. Okay. Now, if you will compute the integral of such a scalar field. Okay? If you're going to compute the integral of such a scalar field, in other words, you're going to compute the line integral of the gradient of a phi over the curve C. Okay? So this should be what? Guess. So it should be phi evaluated at the B minus phi evaluated at the A actually. So from where the curve stops and from where the curve starts. Real quick proof why this is true and why this is valid. Okay. I would like to integrate this f around C. That's what I want. Okay. So for doing it, what I need to do, I need to take my del phi and substitute P of t into it, and I need to take the dot product with the P prime of t. Okay? And integrate this over the A to B and dt. Okay? This is what it's going to be actually. Okay? But I know that this gradient for the scalar field is basically the Fresher derivative actually. Okay? Gradient is the Fresher derivative. Can you predict the answer of this expression actually? So what would be this actually? I mean, if you remember, we did a path property when we were doing the section on the Fresher derivative. We said, imagine you have a path, and imagine you take a scalar field and substitute into a path, so you're going to get a new curve and you take, for example, the tangent vector from the original curve and substitute it into the fresher derivative, you're going to get the tangent vector on the transformed curve actually. If you remember, you did it. So this is precisely the same actually. That, okay, you have phi of t and you are computing the fresher derivative of it. So you are basically sending. Let me get into the details. Okay, let's not be too quick. A to b. Okay, so what this is going to be? So I can say that this is same as a d. Okay, the fresher derivative of phi of p of t. Okay, operated onto what? P prime of t, and the p prime of t can be written as d, the fresher derivative of d, p evaluated at what? P of t evaluated at 1. Remember? So we did this property as well. This is dt. I would like to do what I would like to simplify this expression. So can you guess where we are heading? Okay. So I can write this as a composition actually. Okay. By changing it. So this would be the integral from a to b. Okay. So I can write this as a d of phi composition p, okay, of t operated on 1. Okay? That's what is going to be then. So you have to keep the chain rule in your example. You know, the derivative of the composition of G composition f evaluated at A of h is what? The derivative of G of f of A operated on the fresher derivative of f of A operated on to h actually.
Yes.
That's what it is. Just compare it with this actually. So you have it. Okay. So this is going to be what m. So that's a path, and you are computing the fresher derivative of a path, a transformed path. So what is the fresher derivative of a transformed path actually? In other words, what is the fresher derivative of the path? So I used it here. So I know that if I'm going to compute the fresher derivative of the path, I'm going to get the derivative of that. So this is going to be what? You can see that this is going to be the phi composition p prime evaluated at t and dt. Okay? And this guy is what? This is just simply Riemann integral actually. So this is what? So it's like a phi composition p of t is a function, you know, and it's derived with respect to the dt, okay, and you are integrating with respect to the dt, you know, so like that, you know, dt goes away, you know, and this would be what? So the phi composition of the p, okay, evaluated of t, but evaluated from A to B. Okay, from A to B. I must say, this A is the P of the small a, and this B is the P of the small b, so it's better to call it stars actually. And this A to B is the interval where the path is defined actually. You have to be careful. So what will be this? So phi of P of B minus phi of P of A. In other words, this is phi of B star minus phi of A star. And maybe in your statement you can also change this into the star actually. Okay? To just make them differentiate different from this A to B, otherwise we can confirm A to B. Which A to B is which A to B. Okay? So that's it. So you have it. So in other words, if you know that a scalar field is gradient of a vector field is the gradient of a scalar field, and you want to integrate it along the curve, okay, the integral is not going to depend on the entire curve, it's just going to depend on the endpoints actually. So evaluate the scalar field, okay, at the point B and scalar field at the point A. And which scalar field? That scalar field whose gradient is f actually. Whose gradient is f. Okay. So this is really the fundamental theorem of calculus. Second fundamental theorem of calculus. I don't mention that. This is sometimes called the first fundamental theorem in when you are doing, for example, your one-dimensional calculus. Okay. It's just a notation. ये second कह रहा है, हम इसे first कहते हैं. So we can call it the first fundamental. It's completely fine.